Now we shall discuss on module 3 of this chapter 7 under the title Fundamental Theorems for Bounded Linear Functionals. In earlier module 2, we have discussed on Hahn-Banach theorem. Hahn-Banach theorem guarantees the existence of a bounded linear functional over a non-linear space. So, the dual space, that is x dash, always exists. Now, we shall discuss on applications of Hahn-Banach theorem in this module. In module 3, we shall discuss on applications of Hahn-Banach theorem. The main theorem has already been stated in earlier module number 2, and also we have proved Hahn-Banach theorem over a nonlinear space. The nonlinear space may be over the field of reals or over the field of complex numbers. So, we shall start with an application. Given a nonlinear space over a field K, K may be either reals or K may be complex numbers, and a non-zero member x0 belonging to capital X is taken. Then there is a bounded linear functional capital F over X such that f of x naught is equal to norm of x naught, with norm of f is equal to 1. X naught is a non-zero element in X. The proof runs as follows. Let capital M is equal to third bracket x naught, that means the subspace spanned by x naught, which is a collection of all elements alpha x naught, where alpha is real. Here we are taking the applications over the field of reals. Define a mapping F from a subspace capital M to R by f of alpha x naught is equal to alpha norm of x naught. Clearly, f is linear because the range lies in R. So, f is a functional and it is linear. It can be easily verified that f of x plus y is equal to fx plus fy for all x belongs to capital M, and f of beta x is equal to beta into fx for all beta belongs to over the field of reals and x belongs to capital M. Now, for x belongs to capital M, M is the subspace spanned by x naught. So, any element of M can be taken as x is equal to alpha x naught for some real alpha. Now, modulus of fx is equal to modulus of f of alpha x naught, because we have assumed that x is equal to alpha x naught. So, modulus of f of alpha x naught is equal to mod alpha into norm of x naught, which is again equal to modulus of alpha into norm of x naught is equal to norm of alpha x naught by the norm property norm axiom 2, that is norm of alpha x naught is equal to mod of alpha into norm of x naught, which is again equal to norm of x. So, we have modulus of fx is equal to norm of x. Clearly, norm of f is equal to 1 by the above equation. So, we can say that f is a bounded linear functional on M. So, by Hahn-Banach theorem, we get an extension capital F, that means it is a bounded linear functional of small f over x such that norm of f is equal to capital norm of f. That means there exists an extension capital F on all over x of small f with the preservation of norm satisfying norm of f is equal to capital norm of f. But fx is equal to capital Fx for all x belongs to capital M, because small f is the restriction of capital F and f is the extension of small f. Now, x0 is an element of capital M. So, fx naught is equal to capital Fx naught, because capital F is the extension of small f, but f of x naught is equal to norm of x naught. Here alpha is equal to 1. So, we have f of alpha x naught is equal to alpha into norm of x naught by the definition of small f, and taking alpha is equal to 1, we get fx naught is equal to norm of x naught. So,
capital F x naught is equal to norm of x naught, because f of x naught is equal to small of f x naught with norm of f is equal to 1. So, we get another application. Let capital X be a nonlinear space over a field K. K may be either field of reals or field of complex numbers, and x0 not equal to theta, that is x0 is a non-zero element of capital X, and let capital M naught be an arbitrary positive real. So, there exists a bounded linear functional small f on capital X such that norm of f is equal to m naught and f x naught is equal to norm of f into norm of x naught. The proof runs as follows. Let capital G is equal to third bracket x naught, that is the space spanned by small x naught. That means third bracket of x naught is equal to collection of all such elements T x naught where T is real. So, it can be easily verified that G is a subspace of capital X, that is sum of the two elements belongs to G and product of any element by a scalar, that is real scalar, belongs to G. So, G is a subspace of capital X. Define a mapping phi G to R by phi of T x naught is equal to T into m naught into norm of x naught. So, it can be easily verified that phi is linear, that means phi of x plus y is equal to phi x plus phi y for all x y belongs to G, and phi of alpha x is equal to alpha into phi x for all real scalars alpha and for all x belongs to capital G. Now, for x belongs to G, we can take x is equal to T x naught for some t, because by the construction of G, that is G is a subspace spanned by x naught. So, that is why we can take x is equal to T x naught for some real t. Now, modulus of phi x is equal to modulus of phi of T x naught, because x is taken from G and x is equal to T x naught. So, modulus of phi of T x naught is equal to modulus of T m naught into norm of x naught by the modulus property is equal to m0 into mod t into norm of x naught, as m0 is positive, which is again is equal to m naught into norm of T x naught, because norm of T x naught is equal to mod of t into norm of x naught, which follows by norm axiom number 2. So, is equal to m naught into norm of x, because x is equal to T x naught. So, thus we get modulus of phi x is equal to m naught into norm of x. So, modulus of phi x is equal to m naught into norm of x. So, clearly norm of phi is equal to m naught. So, there exists an extension small f of capital phi over x such that norm of small f is equal to norm of phi is equal to m naught. Hence, norm of f is equal to m naught and norm of phi is equal to m naught, but phi x naught is equal to m naught into norm of x naught. Now, x0 belongs to G and f x naught is equal to phi x naught. This follows as small f is the extension of phi. So, that is why we take f x naught is equal to phi x naught and is equal to m naught into norm of x naught by earlier calculation, and m naught norm of x naught is equal to small norm of f into norm of x naught, because norm of phi is equal to m naught. So, thus f x naught is equal to norm of f into norm of x naught. This completes the proof of this application. Now, we take a problem like this. If capital X be a non-trivial real nonlinear space, that means x is not is equal to 0 vector only, then its first conjugate space x dash is also non-trivial. That means the collection of all bounded linear functionals is also non-trivial. That means there is always a bounded linear functional over capital X. The solution looks like this. Let x naught is a non-zero element of capital X. Then there exists a bounded linear functional capital F on x such that f(x naught) is equal to norm of x naught, as x naught is a non-zero element. So, norm of x naught is equal to 0 and norm of f is equal to 1, that is f belongs to capital X dash. So, X dash guarantees that there must always exist a bounded linear functional. So, which shows that f belongs to capital X dash is a non-zero bounded linear functional on capital X. So, we get another application that for every x belongs to capital X, that means capital X is a nonlinear space. We have norm of x is equal to sup of modulus of f(x) over norm of f, where supremum is taken over all non-zero bounded linear functionals on capital X. The proof looks like this. We find a non-zero bounded linear functional f naught belonging to capital X dash such that f(0x) is equal to norm of x and norm of f naught is equal to 1 by the earlier result. That means, we find a non-zero bounded linear functional f0 in the dual space of capital X such that f(0x) is equal to norm of x with norm of f naught is equal to 1. Now, calculate. Now, supremum is taken over all bounded linear functionals which are non-zero, that is supremum of mod of f(x) by norm of f all bounded linear functionals which are not 0 is greater or equals to modulus of f naught x divided by norm of f naught, because f naught is assumed as a non-zero bounded linear functional. So, it is equal to norm of x, because f(0x) is equal to norm of x is considered. Again, for all f non-zero bounded linear functional which an element of capital X dash, we get modulus of f(x) is less or equals to norm of f into norm of x, because f is a bounded linear functional. So, boundedness property of the bounded linear functional, we get modulus of f(x) less or equals to norm of f into norm of x. So, modulus of f(x) divided by norm of f less or equals to norm of x by the earlier result, that is supremum of all bounded linear functionals over x dash which are not 0, modulus of f(x) divided by norm of f, which is again less or equals to norm of x. Hence, norm of x is equal to supremum of modulus of f(x) divided by norm of f, where f is a non-zero bounded linear functionals taken from x dash and supremum is taken of all such bounded linear functionals which are not 0. So, we take a corollary. If f(x) is equal to 0 for every f belongs to x dash, where f is a non-zero bounded linear functional in the dual space, that is first conjugate space, then x must be equal to 0. It is very simple proof, that is in the earlier result we get norm of x is equal to supremum of modulus of f(x) divided by norm of f, and supremum is taken over all such non-zero bounded linear functionals over x, that is norm of x is equal to supremum of modulus of f(x) divided by norm of x, where f not equal to 0 functional belonging to capital X. This means norm of x is equal to 0. So, by norm axiom property 1, that is n1, we get norm of x is equal to 0 implies x is equal to 0 vector in capital X. So, we take another corollary, that if for every non-zero bounded linear functional f, that means if f is a non-zero bounded linear functional taken from x dash, then f(x) is equal to fy for x y belongs to x imply x is equal to y. So, the proof is very simple. If f(x) is equal to fy implies f(x) minus fy is equal to 0 scalar, as f is linear. So, f(x) minus fy is equal to f of x minus y. So, f of x minus y is equal to 0, because f(x) minus fy is equal to 0 for all f belongs to x dash, and f is non-zero functional, rather f is a bounded non-zero linear functional on x. So, by the earlier corollary we get f(x) equal to fy implies x minus y equal to 0 vector implies x is equal to y. So, we get another application. Let capital M be a closed subspace of a nonlinear space capital X such that M is not equal to X. That means M is a proper subspace of X. Let U belongs to X minus M, that is U does not belongs to capital M, and let D is equal to distance of U comma M, that means is equal to infimum of norm of U minus M, where infimum is taken over all such M belongs to capital M. Then there is a bounded linear functional f belonging to capital X dash with the following properties. Number 1, f(x) is equal to 0 for all x belongs to capital M, f of u is equal to 1 where u is taken from x minus m, and number 3, norm of f is equal to 1 by d, where d is equal to distance u comma m, that is infimum of norm of u minus m, where m is taken from capital M. M is the subspace of a nonlinear space X and M is closed. Clearly d greater than 0. Let n is equal to third bracket M union singleton set U, that means n is a subspace of X and it is spanned by capital M and singleton set U. So, every member of capital N is of the form M plus T into U, where M belongs to M and T belongs to R. R means space of reals. Define a mapping G from N to R by G of M plus Tu is equal to T, that means G is a functional. So, clearly G is linear, that means G of x plus y is equal to Gx plus Gy for all xy belongs to capital N, and G of alpha x is equal to alpha into Gx for all alpha belonging to R and for all x belongs to capital N. Now, Gm is equal to 0 for M belonging to M, because M is equal to M plus 0 into U, T is taken as 0. So, Gu is equal to 1. Because G of M plus Tu is equal to T, and for T equal to 1 we get G of U is equal to 1. For T not equal to 0, modulus of G M plus Tu is equal to modulus of T, because we have assumed that G of M plus Tu is equal to T. So, thus modulus of G of M plus Tu is equal to mod T is equal to mod T into norm of M plus Tu divided by norm of M plus Tu is equal to norm of M plus Tu divided by norm of U minus of M by T is always less or equals to 1 by T into norm of M plus Tu, because we have assumed D equal to infimum of U comma M, as minus M by T belongs to M and M is the subspace. Let capital X is equal to M plus Tu belongs to N, because N is a subspace spanned by M and singleton set U. So, modulus of Gx less or equals to 1 by D into norm of X. In the earlier step, we have obtained that modulus of Gm plus Tu less or equals to 1 by T into M plus Tu, norm of M plus Tu. And if we take M plus Tu is equal to X, we get modulus of Gx less or equals to 1 by D into norm of X. This implies that G is bounded, and that is why norm of G is less or equals to 1 by D. So, G belongs to N dash, that means G is a bounded linear functional over N. Again, D is equal to infimum of norm of U minus M, where infimum is taken over all such M taken from M, where M is a closed subspace of capital M. So, by the property of the infimum, there exists a sequence of elements Mn belonging to capital M such that norm of U minus Mn tends to D as N tends to infinity. Now, modulus of G of U minus Mn less or equals to norm of G into norm of U minus Mn. This has been considered because G is a bounded linear functional. Now, G of U minus Mn is equal to 1. So, 1 is less or equals to norm of G into norm of U minus Mn. Since G of U minus Mn is equal to Gu minus Gmn, Gu is equal to 1, G of Mn is equal to 0. Already we have seen that G of all such elements belonging to capital M, G of that element belonging to capital M is equal to 0. So, Gu minus G of Mn is equal to 1 minus 0 is equal to 1. Letting n tends to infinity, we get 1 by d less or equals to norm of G. Thus, we get norm of G equal to 1 by t. So, there exists a bounded linear functional f belonging to capital X dash, which is again an extension of small g on capital N, such that f(x) is equal to gx, because g is an restriction of small f. For all x belongs to n, we get f(x) is equal to gx with the property norm of f is equal to norm of g. So, thus we have f(x) is equal to 0 for all x belongs to capital N, f of u is equal to 1, and number 3, norm of f is equal to 1 by d.
Up to this, in module 3 of this chapter 7, we have discussed so many applications of Hahn-Banach theorem over a nonlinear space. So, we shall have to discuss another application, so we will discuss in later. Now, before discussion on the further application, we want to talk on application of a real topological vector space. Suppose X be a linear topological vector space and f is a linear function on X, and if A and B are two non-empty disjoint convex subsets of X, and if A is open, there is a linear function on f on all over capital X such that f(x) less or equals to gamma less or equals to f of y for all x belongs to capital A and for all y belongs to capital B and for some scalar gamma belonging to R. Moreover, there is a linear function of small f over capital X such that real f(x) less than gamma 1 less than gamma 2 real f of y for some gamma 1 gamma 2 belonging to R and for all x belongs to capital A and for all y belongs to capital B. But we are not going into details of the proof of this result. So, we shall go on a further application of Hahn-Banach theorem over a nonlinear space. Now, we shall go on another application on a nonlinear space. Let capital M be a subspace of a nonlinear space capital X and M not is equal to capital X. That means, M is a proper subspace of X. If u belongs to x minus m, that means u is not an element of capital M such that d is equal to distance of u comma m having the restriction that d is greater than 0. Then there is a bounded linear functional capital F belonging to x dash, the first conjugate space of x, rather the first dual of capital X such that f of x is equal to 0 for all x belongs to capital M, f of u is equal to d, and third, norm of f is equal to 1. Let capital N is equal to third bracket M union singleton set U, that is the subspace generated by M and singleton set U, that is N is spanned by capital M and singleton set U. Define a function f from N to R by f(x) is equal to t into d. That means, f is a functional, that means f is a real valued function over n, where x is equal to m plus tu, because we have assumed f(x) is equal to td and x can be taken as x is equal to m plus tu for some m belongs to capital M and for some real t. So, f of m plus tu is equal to td by the construction of functional f, small f. Clearly, f is linear. Now, f of m is equal to 0 for all m belongs to capital M. In this case, m plus tu, if we take t is equal to 0, then we get f of m is equal to 0 into d is equal to 0, and f of u is equal to d where t is equal to 1. Now, for t not equal to 0, norm of m plus tu is equal to norm of minus t of minus m by t minus u, which is equal to modulus of t into norm of minus m by t minus u by the norm axiom property 2, which is greater or equals to modulus of t into d by the infimum property of d, as minus m by t belongs to capital M and d is equal to distance of u comma m.
So, modulus of f of m plus tu is equal to modulus of t into d, which is again less or equals to norm of m plus tu, because d is the infimum and m plus tu belongs to capital N. Let x is equal to m plus tu belongs to capital N. So, modulus of fx less or equals to norm of x, which again implies that norm of f is less or equals to 1. Clearly, f is bounded with norm of f less or equals to 1. So, f belongs to n dashed, that means f is a bounded linear functional over capital N. We have d equal to distance of u comma m, that means distance of u comma m is equal to infimum of all such norms u minus m, where infimum is taken over all m taken from capital M. Let epsilon greater than 0. By infimum property, there exists an element small m belonging to capital N such that norm of u minus m less than d plus epsilon. Put v is equal to m minus u divided by norm of m minus u is equal to m by norm of m minus u minus 1 by norm of m minus u into u belonging to capital N, where t is equal to minus 1 by norm of m minus u and m by norm of m minus u belonging to capital M, as M is a subspace. So, norm of v is equal to 1, but modulus of fv is equal to d by norm of m minus u, which is greater than d by d plus epsilon into norm of v, as norm of v equal to 1. In the earlier step, we have obtained modulus of fv is equal to d by norm of m minus u into 1 and norm of v equal to 1. As epsilon greater than 0 is arbitrary, we get modulus of fv greater or equals to norm of v. So, norm of f is greater or equals to 1. So, by the earlier result, by combining, we get norm of f is equal to 1. Hence, there exists a bounded linear functional capital F over x, which is an extension of small f over capital N, such that fx is equal to capital Fx for all x belongs to capital N, with norm of f is equal to small norm of f, that is norm of small f is equal to norm of capital F, and hence we get capital Fx is equal to 0 for all x belongs to capital M, and number 2, f of u is equal to d, and number 3, norm of f is equal to 1. Now, here we shall cite an example that the extension of a bounded linear functional is not unique. So, for this we take the underlying space as R2, that is the Euclidean 2 space over the field of reals. So, let us assume that x is equal to R2, take x comma y belonging to capital X, define norm of pair x comma y is equal to modulus of x plus modulus of y, x y belongs to capital R. It can be easily verified that all the norm axioms as defined above are automatically satisfied, and that is why capital X is a norm linear space with respect to the norm defined above. Let capital M is equal to collection of all such elements, rather pairwise elements from R2, that is collection of all such elements x comma 0, x is taken from R, that is space of reals. So, M is a subspace of R2. It can be easily verified that M is a subspace of R2. Define f from f to R by f of x naught is equal to x. Clearly, f is a linear functional on capital M. Now, modulus of f of x naught is equal to mod x, as defined by f of x naught is equal to x. So, modulus of f of x naught is equal to modulus of x is equal to norm of x comma 0 by the definition of the norm. So, norm of f is equal to 1. Clearly, f is bounded. So, small f is a bounded linear functional on capital M. Define a mapping capital F1 from x to R and capital F2 from x to R by f1 xy is equal to x plus y and capital F2xy is equal to x minus y for all xy belonging to capital X. It can be easily verified that F1 and F2 are linear, that is capital F1 and capital F2 are linear. Now, modulus of F1 xy is equal to modulus of x plus y, because F1 xy is equal to x plus y is defined. So, modulus of xy less or equals to mod x plus mod y. By the definition of the product norm in R2, modulus of x plus modulus of y is equal to norm of x comma y. So, modulus of f xy is equal to norm of x comma y. Again, modulus of f2 x comma y is equal to modulus of x minus y, which is again less or equals to modulus of x plus modulus of y is equal to norm of pair x comma y. So, capital F1 and capital F2 are bounded linear functional with norm of F1 is less or equals to 1 and norm of F2 is less or equals to 1. Thus, we get norm of F1 less or equals to norm of F and norm of F2 less or equals to small norm of F. Now, for all x comma 0 belonging to M, we get F1 x comma 0 is equal to x is equal to f of x 0, that is capital F1 x naught is equal to small f x naught, and capital F2 x naught is equal to x is equal to f of x naught, that is capital F2 x naught is equal to small f x naught. So, capital F1 and capital F2 are the extensions of small f. Now, for all x comma 0 belonging to capital M, small f x comma 0 is equal to capital F1 x naught. So, modulus of f of x naught is equal to modulus of F1 x naught. As F1 is bounded, so modulus of F1 x naught is less or equals to norm of F1 into norm of x naught. So, small norm of f is less or equals to norm of capital F1. Similarly, we get norm of small f is less or equals to norm of capital F2. So, norm of capital F1 is equal to norm of small f is equal to norm of capital F2. This means that the extension of small f is not unique, but it has preserved the norms with the extensions of capital F1 and capital F2.
In this module 3, we have discussed on many applications of Hahn-Banach theorem. There are other applications, but we are not going into details. So, with this we come to an end of this module 3.